Guys, uh, sit down. AJ, sit down. Also, I'm already recording. All right, shh. Guys, just keep in mind everything I do is because I care about all of you and I want what's best for us all. So, shh. No. Shh. All right. So, Last chapter we talked about taking a sample if we were trying to legitimately estimate what the proportion or what the mean was of the population, right? Using the sample to make predictions, to make educated conclusions about the population. And this is actually relatively close to that same process. I've been mentioning for a while. Once you're good at that 4-step process, that's what we do the entire semester, okay? So all this math will be very familiar. We're just going to take a slightly different stance on it. Now, we're not trying to predict, we're not trying to estimate about the population. Actually, this chapter, what we're doing is we're testing people's claims about the population. All right. So maybe a drug company makes a claim about their product. We take a sample and we try to see, do we have evidence against their claim or not? So that's going to be the focus of this chapter. And I actually think this is even a little bit more interesting than chapter 8 because we're diving into what companies actually do, what businesses actually do when they're testing products, anything like that. They make decisions based on claims that are being made and samples that they take. All right. So I think the best way, let's just jump in to see what this looks like, show you what that process looks like. Same thing like in chapter 8. I know a couple of you ended up noticing I didn't do 8.1. Same thing here. We're just going to dive right into 9.2 because 9.1 just has a ton of vocab, interpretation, stuff like that. But they have you learn all of that without the math, which to me doesn't really make much sense. Okay. I think it makes more sense. I just take more time here in section 2 and I embed all those things in while teaching you the actual math along the way. Okay, so let's take a look at this. A current medicine for Alzheimer's is said to have 10% of the population taking it experience nausea. A new drug manufacturer believes that its medication has a lower rate of nausea for its patients. To test this claim, researchers conduct an experiment. They give the new drug to a sample of 300 out of 5,000 Alzheimer's patients whose families who've given informed consent for the patient to participate in the study. In all, 21 of the subjects experienced nausea. Do these data provide statistical evidence that less than 10% of patients who take the new drug will experience nausea? Use a 0.05 significance level. Okay, so now this is kind of the new prompt. If you ever see, do these data provide statistical evidence? That's kind of the new prompt we're looking for to do the 4-step process, but in this fashion. Okay, so like before, it was construct and interpret confidence interval. Now that's our key phrase. That tells us we're going to be doing this process. All right. So the first thing we're going to do, just like we did last time, what was our state step last time? What did it involve? Yeah, naming, right? We want to name our procedure. That's going to be the same thing here, okay? We're going to want to name our procedure. So in naming it, we still have one sample, right? In this case, do you notice we're dealing with percents, right? With proportions. What goes with proportions? Z or T? Z. Okay, so this is going to be a one sample Z. Now, here's the other difference. Chapter 8, where we're dealing with intervals. Does anybody remember as we were searching through the calculator, what else did it say besides interval? What was the other thing? Test. So this chapter, we're dealing with tests. These are called either significance tests or hypothesis tests. You'll hear me use those words kind of interchangeably throughout the chapter. But this time we are performing tests. All right, so this is a one sample Z test for a proportion. All right. Now, for confidence intervals, that was it for the state step. All you had to do was name it. In this chapter, we do have a little bit more we need to do. We're going to set up what we call our hypotheses, which again should make sense to you. You've all had a science class, right? And you know, in order to perform an experiment, to run an experiment, you need a hypothesis that you're testing, right? So math works the same way. We're going to establish what our hypotheses are. You always have two of them. Okay, you have the null hypothesis. The null hypothesis is whatever the current claim is. What is the current claim? For the current medication, what percentage are they saying is true? 10%. All right. So our first hypothesis, we call this the null hypothesis. And we use a little zero down there. So the null hypothesis is that the true proportion is 10%. Then we set up what we call the alternative hypothesis. The alternative hypothesis is what we are actually trying to gain evidence for. What are we hoping to gain evidence for with this new medication? What do we want to be true? We want to show that our new medication has less than 10% have nausea. We represent alternative, makes sense, with an A. And what we're hoping to show is our medication has less than 10% of people experiencing nausea. The other component is we also have to take into account what does this P represent, okay? You can't just throw around a variable without establishing what that variable is. So this P is going to be the true proportion of patients who experience nausea from this new drug, okay? So step a little bit more involved in this chapter, but again, by the end of it, this is going to be like back of your own hand. You'll recognize what to do with it. Oh, what? Can somebody translate? What does that mean? What? Is this where I just smile and nod and pretend like I know what he's saying? Okay. All right. So the next thing we want to consider, okay, the real question here is how rare is our sample, right? If the true proportion really is 10%, how rare is it to get a sample like ours, okay? How rare that is comes from calculating a z-score, okay? So that's why proportions are still with z's, because literally you're just calculating a z-score, okay? Think about it. A z-score is just an observation minus the true mean divided by standard deviation. And you know all three of those components. So you've already worked with all three of those components. Now just putting them together in this fashion, in this context. Okay. So again, we're going to figure out how rare our sample is. Well, our sample statistic was we got 21 out of 300 patients. And I think I already did the math. Is that 7%? If you actually do that math, I think that's where that 0.07 is coming from. 21 divided by 300. That's our sample. Yes? All right. So you take your sample, okay, your observation, minus the true center. Well, what are they saying the true center is? 0.1, right? So they're saying the true center right now, we're assuming it is 0.1. Until we've gained evidence against that, we're assuming the 0.1 is true. All right? Divided by, again, think of this like a z-score, divided by standard deviation. All right? Now, you know how to do standard deviation for a proportion. Isn't this the formula from the packet, right, for standard deviation? Right? Literally, where did it go? Do you still have yours out? Somewhere? Yeah, thank you. This right here, right? Standard deviation over proportion. Now, here's the slight little caveat in this, okay? When we're setting this up, every single step along the way, we need to operate under the assumption the null is true unless we gain evidence otherwise. So when I'm setting up the standard deviation, okay, while I'm setting this up, again, I actually am setting this up assuming the null is true. So the null is actually what I'm putting in here. Okay, I'm not putting my sample, I'm putting the null in there. Okay. And I need one of my calculators now. So square root of 0.1 times 0.9 divided by 300. And I'm going to take 0.07 minus 0.1 divided by that. Now it's going to give me negative 1.73. Okay, so when they say test statistic, really it is just a z-score. All right, yes. There will be in just a second, yes. So don't forget about having to do that. You'll never actually have to do that yourself. I'm just walking through the process now, then I'll show you the calculator. All right, so right now we're assuming that 0.1 is true. We got a sample down here at 0.07, and we want to know how rare is that. Well, what calculator command can we use to find the area under a curve? Normal CDF. So what we can do is we can calculate how rare that is. This is a probability of getting a sample as small or smaller than ours. Okay, so that's what we're going to do. What is the probability that we get a sample at least as small as this one? Okay, so when you calculate that, we get 0.0416. Okay. Now, the question is, how rare are we willing to accept? So we're saying if the true mean is actually 10%, we would have gotten a sample at least as small as ours around 4% of the time. All right. Now, let me draw your attention up to this. Okay. That is saying how much we are willing to accept, okay? We're willing to accept down to a 5% chance of it happening, but isn't this even more rare? Thank you. Even more rare than that 5%, right? This is less likely to happen than we were willing to allow, okay? So what that means is in this case, we would disagree with their claim, right? We disagree that the true percent is 10%. All right. So that's kind of the structure, the outline of how this goes. Now, let me show you formally a little bit more about this. All right. So that value that we found, that 0.0416, all right, we call that the p-value. Okay, so the test statistic is mainly just a z-score that you find. The probability that you find, we call that the p-value. And again, what it tells us is, assuming that that first claim is true, it tells us the probability of getting a sample as rare as ours. Or in this case, I even labeled that out for you so you didn't have to write it yourself. So in this case, what we're saying is if 10% of patients actually do experience nausea, there'd be only about a 4% chance of us getting a sample like ours, okay? Now, again, that's pretty rare. It's only 4% of the time. That'd be pretty rare, all right? So that's gaining evidence, okay? Gaining evidence that that first claim was wrong, isn't it? If this is super rare to happen, we are gaining evidence against that initial claim, all right? So how do we state that? Okay, how do we conclude based on these numbers? Well, what you end up doing is we say that we need to make a direct comparison to the significance level. Now, originally I said that significance level, they labeled as 0.05. And ours is smaller than that, right? Our p-value is only 0.04. It's smaller than that significance level. It's more rare than we were willing to accept, okay? When that's the case, okay, when your p-value is smaller than that level you're willing to accept, that actually means you get to reject that initial claim. Okay, we're going to reject that null statement. And what that means, that means that we did get evidence. Okay, we do have evidence for the alternative. Okay, so if you reject that null statement, what you've done is you've gained evidence for the alternative. You've gained evidence that less than 10% of patients who take the new drug will experience nausea. So when you're writing your conclusions, this is what I'm looking for. Okay, 3 pieces. Make a direct comparison with that number that you find. And again, I'll show you in the calculator. There's a very easy way to get that number. Say whether you reject or you could fail to reject. We'll talk about that in the next example. And then you say what that means you have evidence for. Now, 1 second, don't freak out. I'm going to move the page for a second. I'll come back. Note this language. We have convincing evidence that less than 10%, blah, 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 blah. Is there evidence that less than 10%? Didn't I do what I did last chapter? Didn't I just copy paste that statement saying what I either did get evidence for or did not get evidence for? So same thing I taught you to do last chapter. I taught you just take their own language to use as your context. You're still going to do that this chapter too. All right. So again, just note that's where that is coming from. Okay. That language is coming from their own question. So that's just to give you a little bit of basis on what we're doing. Now let's actually do this as the 4-step process so you can really see how this unfolds. Okay. So our next example. A software company is trying to decide whether to produce an upgrade of one of its programs. Customers would have to pay $100 for the upgrade. For the upgrade to be profitable, the company needs to sell it to more than 20% of the customers. You contact a random sample of 60 customers and find that 16 would be willing to pay $100 for the upgrade. Do these data provide statistical evidence that more than 20% of the company's customers are willing to purchase the upgrade? All right, so again, this phrase, do these data provide convincing evidence? That phrase is what tells us we're going to be doing this process from this chapter. Okay, that's telling us we're going to go through this whole new 4-step process. All right, what happens in the stage step? We need to name it. Yeah, and in this case, whoopsie. In this case, yes, we're doing tests instead of intervals. Okay. So we took one sample, proportions do deal with z's, and it is a test instead of an interval. The one thing to remember, though, is there's actually a little bit more to the state step this time. If we're performing a test, we need to establish what our hypotheses are, correct? So remember, those always come in twos, right? The null, which is the current claim, the alternative, which is the claim that, or what we're trying to show, trying to get evidence for. So what is the current claim? 20%. Okay, so we're going to say that's the current claim. And what are we trying to show? That more than that. Because if we can show that there's more than that, that would make our product or our upgrade profitable for the company. And then you do always have to establish, all right, you have to establish what that P means. You can't just start throwing out a variable and not establishing what it is. So you just want to say that that P is representing the actual proportion of the company's customers who would be willing to purchase that upgrade. All right, now something I skipped over in the first example because I was obviously just trying to get the point across of what we're doing. In the big picture of the 4-step process, what comes next? Plan. Okay, and yes, I know I skipped that the first time because I was just going for the basics of what this looks like, but we are following that same model as we did last chapter. So the next phase would be the plan step. And what do we do in the plan step? Random, normal, independent. Okay, so that's why I said if you're good at last chapter, you will continue to be good at this chapter. Okay, you know what that outline looks like. Random, easiest thing, right? Because don't you just have to look for the fact that they said it was random, right? And they do say you contact a random sample of 60 customers. So, oh, what did I hide here? Oh, random. All right. So random, you contact a random sample of 60 customers. Same as always, right? Normality for proportions. Remember, we've done normalities in a couple different ways. One way we look for we want our sample size to at least be 30. The other way we talk about successes and failures. Which way is the proportion way? Successes and failures. Now, there is one little caveat to that in this context, okay? So remember during that initial example, I said along the way, every single thing we do has to assume the null is true until we can show otherwise. So in this case, it is still successes and failures. The awkward part, though, is they want you to find the expected successes and failures, what you would have expected if the null were true, okay? So what that looks like is our expected successes. Well, we had 60 people in our sample, right? And according to the null, 20% of them should be successful. What do I do with the 60 and the 0.2? Multiply. So 60 times the null, 60 times 0.2 means we would expect 12 successes. Okay? Expected failures. Wouldn't that be the same thing? We had 60 people. We'd expect, according to the null, for 80% of them to be failures. So again, pretty much same process, except you need the expected based on the null being true. You have to assume the null is true until we show otherwise. All right. And what's the last thing I need to know? What am I actually comparing these against? 10. Yeah. So you also want to say, hey, both are at least 10. And what's the last condition that we check? Independent. And what do we say for independence? Less than 10%. Now, I don't just want to say less than 10%. We do want to make it a full statement. So our sample is less than 10% of what? Of all customers for the company, yes. All right, so state, plan, do. Isn't this where we do the math now? Okay, and the math here is answering the question, how rare would this be? And again, a z-score will answer that. A z-score will answer how rare the sample is. Okay, so if I'm setting up the z-score, okay, I want my observation minus the actual truth. Okay, so my observation, didn't we say, how many was it? Was it 16? Thank you. 16 out of 60. So our sample is telling us about 27% of people will be willing to purchase the upgrade. Okay, our observation minus the actual center. Well, what's the actual truth right now according to this problem? Minus 20%. And of course, a z-score, observation minus the mean divided by standard deviation, okay? I think a standard deviation, if you ever need it, isn't that in this packet here, right? If you ever need to recall how to set up standard deviation, it's right here. The thing to remember, just like I said for normality, is every step of the way, you have to assume the null is true, okay? Which one of these do I use then when I make my standard deviation? The 0.2. 0.2, right? You construct everything using the 0.2, okay? You must assume that that is true every step along the way until you show otherwise. Now, Bart asked if there was a program that could do this for us, and the answer is yes. Okay, you don't have to do this by hand. Just like in chapter 8, I want you to set it up for me, but then I want you to let the calculator do all the work for you. Okay? So let's dive into the calculator. So this is going to be the third program that we're learning, third program that we're talking about. And remember what I said last chapter, okay? Again, I've said oftentimes their naming scheme is terrible, okay? Absolutely terrible. But there are a couple things you can do to remember what you need to be looking for. Rule number 1, if you're dealing with a proportion, it absolutely has to say proportion in its name, okay? So that's rule number 1. Whatever we're looking for, we know for a fact must have proportion in its name. Proportions deal with what? T's or Z's? Z, okay, this is a test, and we took one sample. Which one of these references everything I just said that it needed? 5. One proportion Z test. Okay, now let's take a look at what this looks like, because obviously it's going to have a slightly different look than the interval command. The first thing it's asking for is this thing called P naught. Okay, now you've seen that little subscript 0 before. What does that remind you of? It reminds you of the null. Okay, this is asking you for that null value. What is the current claim? Well, the current claim right now is 0.2, isn't it? Is asking now your sample. How many successes out of how many total? So how many successes did we have? Out of. Now it's asking for the direction of your alternative. Okay, so your alternative statement. Are we looking for something to be less than, greater than, or simply not that 0.2? What did we say we were doing? I think greater than, right? So then you would make sure it's highlighted greater than. Then calculate. Boom. You can actually get it to sketch a normal curve for you and shade that normal curve for you. We actually never use that function. It doesn't really serve much purpose, but it's like a visual of what's happening. All right, and here you go. So a couple things, all right? This Z right here is that Z we were trying to find. Okay, so that is what we actually just finished setting up. So where you said Z equals that big mess, now that big mess equals this. Okay, so what you just wrote, now say that that equals 1.29. All right, and then that normal CDF thing we did, that probability of this actually occurring, that is this right here, what we call the p-value. Okay, so this is our p-value, okay, 0.0984. So these are going to be the two things you're always looking for when you run the program. These are the two things that you're going to be writing down for me on your paper. Does somebody have that down so when I switch you can read it back to me? Yeah? Okay. So this is 1.29, and then you're going to say our p-value is 0.0984. Thank you. Did I copy it down wrong? No? Oh, you're looking for greater than. You typed in the wrong direction to the command. All right, now, looking at this. So remember, in the conclusion, now we have to decide, is this enough to reject the null hypothesis? Or is this not enough to reject the null hypothesis? So here, previous page. Here we specified that we were willing to accept 5% random variability. Okay, that's what that significance level is. And before, on that first one, we were more rare than that, right? We were more rare than we were willing to allow. So we ended up rejecting the null, saying, all right, this is too rare to have happened just by random chance. All right, we're rejecting that null. This time, do you notice we're bigger than that 0.05? right? We're not as rare, right? This actually isn't as uncommon. Can everybody see that? So if it's not as uncommon, okay, as we were willing to accept, in this case now, we don't have evidence to reject the null. We phrase that as failing to reject. Now, some kids find that language a little bit awkward, that the only two things we can decide are to reject or fail to reject. Never, ever, ever use the term accept. Okay, you never accept the null, you simply fail to reject it. The way that I help kids understand why we use that language is think of a court of law. Do you ever decide someone is innocent? No, what do you decide? What does a jury decide about that individual? Not guilty. They don't say that they're innocent. They never, ever, ever say they're innocent. They just say they're not guilty. We don't have enough evidence to say that they are guilty. Okay? They don't say that they're innocent. Same thing here. Okay? It works exactly that same way. You never say you agree with the null. You simply say you don't have enough to reject that null. Yes. To see if their product works. Well, actually, so oftentimes the company will do these tests themselves because they want to know, is our product better than what's already out there? So actually, honestly, usually they hire a statistician and they do this themselves because they want to know if they make a product and it's not as good what's already out there, they're going to lose money by making that product then. So usually this is actually them doing it themselves, not some random statistician just attacking that company. Like they want this data themselves. Because again, if they make a product that's not as efficient as what's already out there in the public, why would they waste their time? They're not going to make money off of it. Oh, okay. So when you fail to reject, the only difference in this is now you insert by saying you don't have evidence. And then you just copy everything that was in the prompt. Okay? So again, if you do reject, you have evidence towards whatever you were claiming. If you fail to reject, just insert that you don't have evidence, and then you just copy and paste everything like we did before. So I think, do I only have one more example? Then, ooh. And we probably won't get to the multiple choice. We'll see. All right. Just again, I think the best way to get good at this is just modeling how this works because this is relatively new. So let's do this one more time. If we run out of time, I may end up skipping the multiple choice and saving that for a conversation tomorrow. All right. So a study of classic authors uncovered a distinguishable speech pattern that differed from author to author. Plato utilized this pattern 21.4% of the passages in his works. The owner of a rare bookstore claims to have an original Plato work, but you suspect this speech pattern occurs too frequently to be an original Plato work. A random sample of passages from the work in question was taken, and it was found that 136 of the 439 selected passages followed the speech pattern. Do the data provide convincing evidence that the work was not written by Plato? All right, so again, here's our key phrase that tells us we're doing what we're doing this chapter, right? That tells us that we're using this 4-step process during the whole thing. And state step. How do we always start? Yeah, we name it. Okay, next chapter, I'll dive more into why that name is so important. Okay, you'll see that in chapter 10. Right now, just know to keep doing it. Okay, and then I'll tell you why we've been doing it all along when we get to chapter 10. The new part of the state step, though, for this particular chapter, what else do we have to establish? Our hypotheses. All right, so our null, what's the current claim? What? 21.4%, or we always change it to its decimal form whenever we're going to be doing math with it. And then in running this test, what are we trying to show? What do we think is true? Okay. In terms of the direction here, so we need a direction. You suspect that the speech pattern occurs too frequently to be a work by Plato. So here we think this particular passage is actually using that too much. It's too frequent to have been an authentic Plato work. So you do have to dive a little bit into the context and the phrasing of the question to sometimes figure out which direction this goes. If it's greater than or less than, comes from the context of the question. Okay? And then because we're throwing out this variable, don't we also have to establish what that variable is? Right? So that variable is going to be the actual proportion of passages in the work that uses that pattern. All right, plan step. All right, so in the plan step, we talk about our conditions. What's our first condition? The easiest one? Random. Did it say? Yep, random sample of passages. So again, that one is super nice and easy. Just remind them that they told you that it is random. What's the next condition? Normal. And for normal, remember, sometimes it's greater than 30. Sometimes it's successes and failures. Which version is proportions? Successes and failures. What's the little caveat to that, though, in this chapter? Expected successes and failures. Yeah. So we sampled 439 passages, and they're saying we would expect 21.4% of them to be this pattern. All right. So if I multiply 439 times 0.214, that gives me expected successes is 93.946. And then the rest of them would be our expected failures. And I should unveil. Oh, whoopsie. I don't know. There we go. So this is checking for normality. And what number are we comparing these against? 10, okay? So do remember you're also always comparing these to 10. And the final condition? Independent. What do we say for that? Yes. So we're going to say that it's reasonable to assume this our sample is less than 10% of all of the passages in this work. Right. As far as I know, they actually like to see the exact value, so I actually wouldn't round or at least go to one decimal. Because sometimes they don't like if you shift something to an integer when you shouldn't be. So I would say actually leave it in this case. All right, do step. So remember, the point of this is we want to figure out how rare is our sample. right? And doesn't a z-score answer that question? A z-score will tell us how rare this is. So z-score is based on our observation minus the truth, okay? Well, our observation, what was the sample? 130. 136. Thank you. So our sample was 0.31 minus the truth. Well, what are we saying the truth is? 0.214 divided by standard deviation, okay? Now, when making the standard deviation, remember, you have to assume that the null is true, okay? Every step along the way, you're operating under the assumption that the null is true until you've gained evidence otherwise. And now let's go use our command so we can do all of this for us. And which command is this again? What are we going to be using this section? One proportion z-test. So they want the null. They want our successes out of how many in general. And in this case, once again, don't we believe that we're testing to see if it should be bigger? Right? So you always look for the context. This is always based on your alternative. And then calculate. So here's our z-score. All right. And what about this? What does this mean? Yeah. So this is really 0.0000049 for our p-value. So what do we think? Is that going to be smaller than our significance level? Oh, yeah. It's basically 0, isn't it? So remember, okay, so this was 4 point what? 89. P-value 0.1, 2, 3, 4, 5, 6. There we go. And in our conclusion, remember this time our conclusions come in 3 pieces. A direct comparison to the significance level. So we're going to say our p-value is definitely smaller than our significance level. Did it say this the significance level this time? I can't remember if I stated it. Yeah, okay. If it ever does not say, assume it's 0.05. Okay, common ones are 0.01, 0.05, and 0.1. If they ever don't specify, 0.05 is like the go-to. All right, so just a heads up, sometimes you'll see it not stated. Go with the 0.05, all right? And in this case, our p-value is essentially 0, which is less than that significance level, which we use alpha, which unfortunately my computer doesn't do, which is less than that significance level, so we do reject the null. That means there is convincing evidence that the work was not written by Plato. When you reject the null, you have evidence. When you fail to reject the null, you don't have evidence. Now, sometimes you'll see also a question to interpret the p-value. Okay, so interpreting the p-value is different than your conclusion. So remember the p-value is assuming that the null is true. It tells you how rare your sample is. Okay, so when we're trying to interpret the p-value, first of all, what does it mean for the null to be true? What is the null in this case? 0.214. Yeah, so the null being true would be if the true proportion really is 0.214 of the times that this pattern exists in this work, there is this percent chance of getting a sample proportion at least as big as ours. So again, that's why we reject the null, because it is so utterly rare that this would happen. Now, I am going to cut us off because I want to make sure I have time to pass out your stuff to you. We'll pick up tomorrow with um, with those two multiple choice questions. But I want to make sure I get you your homework, and then I want to make sure I get you that multiple choice packet. Start working on those. Here's this, and then I'll also give you your multiple choice packet, so you can slowly be working on it. The yellow. That would be really cool. I said, what about writing on it for you guys? Like my ink, like I could type that. How would you guys write on it? I forget everybody's gel pens.
Yeah, exactly. If you lose your gel pen, you gotta cover it.
You're welcome. Oh, thank you. Also, the homework for today is literally only the first page front and back. That's it. I was generous today. I also, I spent 4 days on this before we even get to the review of section 1. Well, I spaced it out because now there's a lot of recap of like talking about the errors, like what was wrong, talking about the powering. Oh, there's that third version of like what this not equal to, how that relates to conflict intervals. I'm like, this is like, we need some time here. Oh yeah.
Their record is 20.
They're good.
They're all being nice.
So what was the reference for you guys last year? I feel like you used like you were trying to reach the 500.
Yeah, we were
Like hovering.
a little under.
I still remember that's what it's called, to be 50-50. I'm learning.
These are last thing charges for the AP test.
Because we have some comments. I did this for you guys. Oh, I went to the first class.
Oh, I was just curious. I don't. Oh yeah, there's
I love it. Have a great day, everybody. Oh, would it be possible for you tomorrow? Because I have to give a presentation to the staff, and then I have school to do. So today's a little bit messy. But if you could do it tomorrow, that'd be awesome. You're welcome. I love this stuff so much. Well, and then tomorrow, I actually enjoy because we get into the why a little bit more. Like you talk about the errors, like, well, why would we do this? Like, why do we care about all of this?
Right.
Which is obviously the fun day of like, because that's what kids always want to know. Is, so why are we doing this? Oh, I have reasons. Don't you worry, kiddos.
Well, enjoy your M&M's flash.
Yes, thank you so much.
No problem.
I appreciate it.
Happy Valentine's Day.
Same to you.